Okay, we're going to move right into our afternoon panel. George, if you would, here. Our session leader for this panel is my colleague, George Hirosaki. He is the A.J. Hartsook Professor in Chemical Engineering here at Rice. He joined the Rice faculty after a long distinguished career at Shell Development and Shell Oil Company, and his research focuses on fluid transport through porous media. No, I'm not going to go into long description, fluid flows, right? He works with a industrial consortium. Many of you work with him, U.S. Department of Energy, and it's a pleasure to have George introduce the next set of speakers.
Thank you. There have been many mention of new technology as a solution throughout the day. Now we'll have a session on technology. The title of it is Managing Risk Through Technology, Engineering Challenges to Deepwater Drilling. We'll have 4 speakers from both industry and academia. And the format that we plan to use is that I've asked each speaker to give like a 15-minute presentation. Then we'll take just 1 or 2 questions on that topic just for that speaker. Then after all of the speakers have spoken, then we'll ask him to come up here and then jointly as a group have you to ask whatever questions about technology you would ask the panel. And then they as a panel can respond to your questions. And so you may want to keep the more general questions in mind and reserve the specific questions just after the speaker. So the first speaker that we have is Gene Beck, who is the Stephen Holdridge Faculty Fellow in Petroleum Engineering at Texas A&M. So Gene.
Good afternoon. I feel like I drew the short straw just a little bit, being right after the keynote lunch address, but I'll do my best to make a few points for you today. Hopefully I can get the projector running in the right direction too. I'm going to come today, this one. Okay. I'm going to come today from a perspective of a drilling engineer. Although I'm at Texas A&M right now, I really had just ended or coming out of about a 25-year career in the oil industry as a drilling engineer and operations manager, things that I still do. And I've spent quite a bit of time, of course, looking, curiously over what happened on the Deepwater Horizon incident, and how such a thing could happen. And, where did it go wrong, I think is obviously one of the key questions we're still studying. Those answers are still out. But I do want to share some thoughts, specifically about the blowout and, where it leads us in terms of future technology, and some thoughts I have on that, and the regulatory environment, which I think is going to be critical going forward. I think one comment I would like to make regarding the director's comments, I do not see the Deepwater Horizon incident as a 1 in a million incident. I don't believe that. I think with the way the blowout occurred, that there are probably many other opportunities for similar events to occur, and that we're going to have to be very, very thoughtful going forward to make sure that we design those opportunities out of our drilling sequence. So with that in mind, there we go. Drilling engineers by nature are simplistic because a lot of times what we do is so complex we have to simplify it to get our arms around it. Looking at a failure, looking at a failure like the Macondo well, usually in my mind you see 3 components to a failure. One of them would be a design, and I'm talking about design of specific equipment or materials that did not meet or function under the conditions that they were either foreseen to function under or designed to function under, because those conditions were different than what was foreseen, or errors in the design. Another critical parameter is a flaw in the process, and the process would be how do you assemble the plan and the sequencing for going through a very complex operation like drilling a deep, high-pressure, high-temperature well, and particularly complex if you're doing that in a deep water environment. And then finally, there's a possible human error component, which quite often is very big. Now, when you look at this simple diagram, the mirror image of this diagram are the components to success, right? What are the components of success? A good design, good product that you're using, a good process that you're using to assemble the products, and then, of course, execution, right? Flawless execution. And so those things are pretty critical. And what I want to do is take a look in terms of those simple concepts at what apparently went wrong, I think, on this well, and then how do we go to build our practices going forward to try to keep this from going wrong again. Okay, first off, and this one has been overlooked and maybe not stated as clearly as I'm stating it right now, okay, the float equipment failed in the well. To me, that's very, very obvious as a drilling person. The float equipment failed. If the well blew out up the casing, the float equipment is there as a barrier, and it failed, okay? Why did that happen? Is there a design flaw in that float equipment? Okay, were there process flaws that were involved in the selection of that particular piece of float equipment, right? Did something go wrong there, or was there simply a human error in the installation of that float equipment that kept it from working properly? Okay, when the float valves in the shoe track don't work following a cement job, okay, that is not a good situation, and it's even worse when it goes unrecognized, which is apparently what happened in this well. Okay, so there's one barrier compromised. Okay, did it cause the incident? No, it's the kickstart to the incident right there. Okay, okay. The second one that I have listed here, okay, a barrier was removed without having another tested barrier in place. Now, throughout my career, that's how I was taught, or what I was taught to not do, right? I mean, one of the fail-safe practices and processes that we have to follow as a drilling engineer is to make sure that if you remove a barrier from a well, there's another barrier in place before you remove it. Okay? That's a process, okay, that you have to follow to make sure that works right. Okay? And that clearly failed in the Macondo. Okay? And that one is a pure process error. The sequencing of removing the drilling mud from the well and putting seawater in place was wrong. And that's a very severe flaw. Now, as I'm going to show in a little while, these are issues, when you start having process issues, these are issues that at some point the regulatory assistants or agencies have to come in and help prevent these types of process flaws. Okay. And when that happens, when the drilling mud begins to be removed, okay, you've already compromised one barrier in the float equipment, you take the drilling mud out of the well, the last barrier in the well becomes the blowout preventers. Okay. Now, another major failure, the kick detection in the well failed. Okay. An ounce of prevention is worth a pound of cure. The industry is taught, drilling people are taught, identify kicks early, keep them small, you can handle them, you don't have to deal with high pressures when you're dealing with it, when you're doing that, or much lower pressures. What happened with the kick detection? A major piece of the incident that allowed the whole process to escalate quite quickly from a situation where the well could be underbalanced and flow to where it was underbalanced and began flowing. And I think that the magnitude or the lack of kick detection that allowed the incident to go on for so long before any attempt was made to control it is probably integral to the failure of the BOPs as well. Okay, because the BOPs were then asked to start performing in conditions that were very, very severe. And I'll talk about that again, of course, in a second. And then finally, the BOPs failed. Now this, from my perspective as a drilling engineer, okay, and a man that's been on the rig as a company man and has had people working for me, you know, that I've known for years as company men, that's a very terrifying thought to have a BOP fail on you, because that is your fail-safe. So my question really is, what happened with the BOPs? I don't know that answer yet. I haven't seen any study outcome, you know, of what happened with the BOPs, but it's a very, very worrisome topic that you went to function the BOPs and they didn't work, okay? And of course, in that system, okay, is there a design flaw? We need to know that. Is there a fundamental design flaw in the way the BOPs were thought out that doesn't work in deep water subsea environments, okay? Was there a process flaw? Were there process flaws in the way those BOPs were tested? You know, are we testing our BOPs correctly? And that's a comment I'll further in just a second. And then, of course, finally, is there a human error component? And I would say in both of the cases of the kick detection and the BOPs, the kick detection, I think primarily human error and process error, probably equal amounts of both of those. Okay, but with the BOPs, I think design and process are probably the two key points of those failures. Of course, what happened now, multiple successive failures, and people said this from day one of the blowout. You know, this wasn't one thing that went wrong. There were multiple successive failures that led to this disaster. And these are the four, you know, successive failures that happened in my mind. And this is not an overly complex set of conditions that led to the blowout. Okay, this is actually a fairly simple explanation of what went on that led to the blowout, other than the BOP failure. Okay? But if you look at it, there are design flaws, there are process flaws, and there's human error every step of the way that let us get to the point of the blowout. Now, jumping ahead, we want to address technical challenges, okay? Without listing, you know, 25 or 30 technical challenges, I just wanted to talk about one, the blowout preventer. And the one question I have on the blowout preventer stack, you know, is a subsea blowout preventer, or the systems that we use today, are they suitable for drilling in frontier deep water environments, like we're going to ask them to do? Okay. Well, this gets into, you know, how do you know? Well, the way to know is to test. Well, how are we testing our BOPs? Okay. Traditionally, BOPs, of course, are not tested to failure. They're tested to success, right? They're tested to a working pressure, because if you tested them to success, you'd never be able to drill. You'd be always repairing them. There has to be a point in time, of course, that we subject these BOP systems to more rigorous tests to failure, okay, so that we understand the long-term implications of a successful pressure test. Okay? And we can't just do that at surface conditions, you know, in a shop in Houston. We're going to have to come up with a way of testing these BOP systems in conditions of pressure and temperature that they're going to be functioning at the seafloor. That is a huge challenge, of course, because how do you go create conditions of, you know, 35 or 40 degrees and, you know, 2,000 to 5,000 psi of pressure? To have a physical facility to do that is a challenge. But I think that's one thing that we are going to have to do as a group, is come up with a way of getting the subsurface equipment tested under the conditions that it's going to function at. And then I think we need to rethink our entire testing program, so that when you do a function test on a BOP or a pressure test on a BOP at the field level, you have some good idea of what the meaning of that test is. Okay? How many more times is it going to function successfully? For how long a period of time is that pressure test going to be applicable? Okay? So that's one of the main thoughts and technical challenges, and this is a huge technical challenge to come up with a system to be able to test this equipment like that. Okay? The thought concurrent with that goes back to the overall planning process on a well. You know, blowout preventer is a fail-safe. But if you hook a 15,000 PSI blowout preventer up to a 5,000 PSI rated piece of casing right below it, it doesn't do you a whole lot of good to have a 15,000 PSI blowout preventer. And then when you subsequently test that blowout preventer to 5,000 PSI, because that's the rating of your casing, you're actually, in my mind, diminishing the functionality of that blowout preventer. Okay, they need to be tested to their working pressure over and over and over. And I don't think we have good systems in place in the field. Okay, and in the way we drill these wells, that's an impossibility to do with the way the subsea wellheads are built. And I think we need to make some modifications to those. But a blowout preventer is part of a big system, the entire well plan. And the entire well plan has to be assembled in a manner that allows a plan to work to contain the formation pressures that are being encountered. It's not just the cap on the well, it's the entire well. Okay. Regulatory challenges. What are the regulatory challenges? Okay, if you look at the three things I mentioned, design flaws, process flaws, and human error, that can be rapidly translated to testing policies and processes to help with design flaws, operational policies, practices, and guidelines for process flaws, and then training requirements and certifications for human error. But I think one of the biggest challenges for our regulatory agency is going to be able to staff themselves with people that have similar skill sets to the people they're regulating. That's going to be very, very hard to do, but I think that's going to be critical. Okay, in a conclusion slide, one question, can deep water exploratory wells be safely drilled? Yes, we've done it. Okay, there are a number of people sitting in the room say, I do this every day. Okay, is it 100%? No, I don't think so. I think there are people out there that don't have the capacity to do it safely well after well after well. And I think that we're going to have to work with the government, with regulatory agencies, okay, to get the reliabilities in our designs, in our process, and in our people up to speed to make sure something like this never happens again. Thank you very much.
Thank you, Gene, and we'll have questions for the entire group at the end of the session.
Thank you.
The next speaker we have is Clay Vaughn. He's the Vice President of Deepwater Projects, Exxon Mobil Development Company.
Thank you, Dr. Hirosaki. And I'm pleased to have the opportunity today to discuss with you the Marine Well Containment Company. And I'll refer to it as MWCC as we go along. I'm pleased about that because I expect many of you, if not most of you, share the high level of interest and strong desire that I do to see the deepwater drilling activity resume in the Gulf of Mexico. The Marine Well Containment Company offers an adaptable and effective, we believe, flexible system to respond to deep water well control events that may occur in the future. And will serve, we believe, as a solution to meet the containment capability requirements that are now part of drilling permit application requirements. The MWCC utilizes the vast experience that our oil and gas industry possesses. It utilizes that know-how and it utilizes that technology. It is formed through industry collaboration, and it's open for membership to all oil and gas operators in the Gulf of Mexico. My comments today, hopefully, and the material I'll share with you, hopefully, will raise your level of awareness and understanding in two areas. One, the company itself, what it is, why is it there, And in the second area, the system, the containment system that this company is tasked with managing and deploying. And with that, let me go to my first slide. Assuming that I can, there we go. The objectives of the company, the MWCC, are to provide a rapid response system to address a potential deep water blowout or well control incident in the Gulf of Mexico. It is also there to establish and maintain an organization to assure that the equipment that's part of the system is operational and ever ready for rapid response. It'll operate as a not-for-profit standalone organization. The company has been formed, has 5 current members. You see them on the slide: BP, Chevron, ConocoPhillips, Exxon Mobil, and Shell. And while we have 5 members today, as I mentioned earlier, membership is open to all Gulf of Mexico operators. And each member has an equal share of the company ownership and commits to their proportional share of the system development costs. Obviously, as a member, you have access to the assets of the company and the containment system itself. But I need to mention that it's not necessary to be a member. The access to the equipment will also be provided to non-members through a per-well fee mechanism and obviously an agreement, a system services agreement. But nevertheless, our hope is and expectation is that we'll have more than the 5 represented here as we go out in time. The initial estimate for the complete system development cost is near $1 billion to design and then construct with proven technology the assets necessary for a long-term approach to well containment response. Exxon Mobil is leading a project team that's tasked with the development of that system. It's about 100 people today, and their work will go out into 2012. That phased approach is in 2 parts. First, a lot of effort initially on an interim containment response system, where we've configured assets that we believe can be effective in a response soon. We're following a very deliberate process to assure that their operability and their suitability, and we believe that they'll be ready for deployment soon. And the expanded response system, which runs out into early 2012, and I'll describe the elements of each of these on a later slide. Over time, the system is capable of being expanded and adapted as technologies evolved and may require future investment as we go out in time. But it's being progressed in a way where the capability can be expanded as the need for going into deeper water evolves in the industry. Let me first talk about the interim containment response system. You'll see the key components listed on the slide of this system, and I won't go through each one in detail, but let me describe them as being one of 3 categories. They're either components that are owned by the Marine Well Containment Company. They are either components that are available through specific call-off contracts that the Marine Well Containment Company has with equipment providers or service providers, or they're provided through mutual aid among the members of the company. And you'll see an example on the slide, the 3 mutual aid drill ships with topsides producing capability are under contract to members of the Marine Well Containment Company, and those members attest that in the event of deployment that they will provide those to the incident owner or the company with the need for response through that mutual aid. The capability of the interim containment response system is up to 8,000 feet of water. It will have a 15,000 PSI working pressure capping stack. You see a depiction of that stack on the slide. And And in the 3 mutual aid drill ships, there are storage and processing capacity of up to 60,000 barrels of fluid per day. Dispersant supply, a dedicated dispersant supply, will be part of this system and will be available for rapid deployment. The expanded response system have similar, and I should say that some of the equipment that is in the asset inventory for the interim response system obviously will move to the expanded response system as we get other assets for that system built and ready for deployment. But one main difference are the capture vessels. In this case, for the expanded response system, the capture vessels are dedicated vessels, where before the drill ships through mutual aid. In the expanded system, we'll have 2 modular capture vessels. I'll speak in a bit more detail about them on a later slide, but they are dedicated for the service in the expanded system. They'll obviously need to be modified for topsides processing facilities, and that's part of the scope in the project development of the expanded system. This system will have freestanding risers and manifold systems, and that will enable it then to operate in deeper water depth. It will also have a 15,000 PSI subsea containment assembly. In the expanded system, that assembly is a 3-ram or a 3-preventer type capping assembly. In the interim system, it was single. And the storage and processing capacity in the expanded system is up to 100,000 barrels per day of fluid. And again, the dispersant supply is dedicated and available within this system as well. I mentioned, or I used the word flexible in an earlier statement, and that can be indicated by at least a component here that's shown on this slide. This is a depiction of the ultimate expanded system capping stack. And the idea is that we will have adaptation for this capping stack to be configured or mated to whatever the conditions may derive on the day of deployment. It will provide a means to re-enter the wellbore. It will have port for injection of dispersants or hydrate inhibitors, and it'll have connections for pressure temperature monitoring devices. And obviously we'll have containment type preventers in the stack to allow for a possible shut-in completely. I spoke briefly about the capture vessels in the expanded system, and again, this is a depiction of what that will look like, or similar to what we envision. In that system, again, there will be 2 dedicated modular capture vessels, which normally are in operation, lightering service operation in the Gulf of Mexico. And in fact, when not needed for response, obviously, they will continue in lightering service in the Gulf of Mexico. Some modifications are required, namely dynamic positioning systems, and these vessels need to be outfitted with topsides, appurtenances to accept processing modules that then connect up to subsea riser systems that allow the contents to flow to the capture vessels to be separated, the oil and gas separated, the gas flared, of course, and then safely store and offload that oil to a shuttle tanker. The shuttle tankers are not part of the system. The shuttle tankers are envisioned to be provided by an incident company. And but nevertheless, the capture vessels will be configured in a way to allow the connection to and offloading to Jones Act compliant shuttle tankers. And clearly, to operate in the Gulf of Mexico, we need to be configured to manage weather events such as hurricanes. And these capture vessels will be outfitted in a way where quick disconnect can be managed safely, reliably, and without additional incident complications to move away from the weather-affected area and get the crews to safety. Well, that's a quick run-through of what the company is about and the system that the company is is interested in and also diligently working toward. And our view is that the company and that system will provide us a solution to meet the containment requirements and response requirements that we see in our drilling permit application requirements today. With that, I'll gladly take a question or two. We have time for that? Okay.
Have any question? Clay John Simon with Test. Earlier, Director Bromwich told us that the MWCC is not there yet, right? So can you share with us the specifics of your conversations with that agency?
And where the gaps are and when you'll close those gaps and be able to demonstrate to them that you have that response capability.
First, let me say that we've been working very closely with the BOMer. It's hard for me to say that. I'd rather say BOEM, but with BOMer, we've been working very closely with them throughout for two reasons. One, to keep them abreast of our status, but also to get their feedback and incorporate that feedback into the development of our system. Those engagements have been very productive. We've, as recently as earlier this week, we're speaking with the agency in Washington. We're following a very deliberate process to assure that the assets within the interim response system and ultimately the expanded response system are suitable for deployment, they're appropriately tested, and we can offer a reliable deployment operation. That process is ongoing now. I expect that it'll be completed soon, but we won't offer it for deployment until we're certain that we have the capability that we say we will on the day. But I expect it to be soon.
Two questions, quick answers. First, between the time that a blowout occurs and the time you deploy, what time lag do you anticipate?
Our objective is to begin deployment within 24 hours. You can imagine that there's longer periods of time for certain assets. The containment cap assembly, one of the more, rapid deployment components, the riser systems, the subsea manifolds, over a period of a couple of weeks. And then if capture is necessary, then the vessels in that 2 to 3 week time period.
Second question, if you had a request to go somewhere outside of the Gulf of Mexico, have you anticipated that request?
Have heard that request or have heard questions around that, but this system is designed for and dedicated for the Gulf of Mexico.
Thank you. Thank you, Clay.
All right.
The next speaker is Eric Larson. He is the Vice President and General Manager of Schlumberger North America Offshore. So, Eric.
So for those of you that study circadian cycles, you know that we're getting to the time where you should all go to sleep. And I promise, well, how should I say this? I don't promise to keep you awake, but I do promise to finish on time, so you can set your alarm clocks accordingly. So I'm going to talk a little bit about managing risk with technology, but I thought I would start off by repeating it just very briefly, if I am successful here, some of the comments from earlier this morning. Let's see if we can get this to go. I pushed that button, I promise. So I think we heard very succinctly this morning about what's at stake when it comes to deep water. And you can see the remarkable growth on the left-hand side of the plot there of deep water production from the turn of the millennium on through where we are today. And this particular graph is forecasting off 5 years into the future as well. On the right-hand side, a little bit difficult to see, but I can explain it very quickly. This analyst is forecasting that deep water will contribute about 25% of the incremental net oil production over the next 5 years. So there's a lot at stake, as it was said this morning. With regard to technology, when you look at the graphs that I showed you on the previous slide, particularly the one on the left, you could come to the conclusion that this is, a new industry, and in fact, it's not. It's been around, the offshore industry has been around since before the turn of the last century, 1897, as you can see, and even earlier than that, actually. And as pointed out this morning, nearly, or just over 60 years ago, the first well was drilled out of sight of land, which was a very important point in the offshore industry. So where are we at today? To me, the technology that we're using offshore is extraordinary. I mean, really what the industry has been able to achieve is absolutely remarkable. A state-of-the-art development today would be in 8,000 feet of water. It would be with 20 or more wells, subsea wells, pressures at the reservoir, I might say, not at the wellhead, 20,000 psi and greater, and depths certainly over 20,000 or 25,000 feet. So there is obviously a lot of challenges involved in offshore deepwater drilling, and we chronicled some of those earlier today. I should point out that the sector of the industry that I'm involved with is very much the subsurface. So the company that I work for, we look very much at subsurface. And the challenges that I've detailed on this slide, which you can read, are very specific to drilling, and they don't encompass challenges around some of the exploration activities, development, production, long-term life of the well. But as you look through some of the challenges, and in particular on drilling here, you can see there's an awful lot that faces the drilling engineer, as we heard earlier in the sessions. And in this particular case, for example, we might be required to drill through thousands of feet of salt. And as we exit the salt, we go into a different type of formation, often a rubble zone, and often a zone that is of lower pressure than what's required to drill through the salt. And as a consequence, you end up with significant losses of mud, and that's just one particular example. So in the context of the panel that we're in right now, I thought I would describe at least one technology, and maybe a little bit different direction than some of the others have taken, that I believe that can help manage and mitigate risk in deep water operations, and that's the ability to understand what it is that you're going to face as you're drilling through the formations. In other words, the ability to plan, to map out, to look ahead, and understand precisely when it is that you're going to hit one of these transitions where things may be overpressured or underpressured, and may eventually result into issues that require a sidetrack, or worse, maybe an abandonment of the well itself. So one of the technologies that is often touted as one of the most significant game-changing technologies in the industry, and certainly I think there's very few in the industry that wouldn't rank it in the top 10, is 3D seismic technology. And that's the ability to send acoustic information, or signals, if you will, sound waves, through the formation, or in the case of the offshore environment, through the ocean, and then also through the formation. And then that sound, if you will, bounces off all the various formations or the strata that's underneath of you, and sends back thousands, millions of signals to an array of receivers at surface, or geophones as we call them. And that information is compiled, it's analyzed with a series of complex algorithms, and with the information we can construct a picture of what it is below us before we ever go there. And the real the value of this has been that we can identify structures which might be hydrocarbon bearing, whereas many years ago we would drill true rank wildcats, which is blind drilling. And in this case, we have a much better chance of hitting the target. There's a lot of other useful parts of this information, but it's still on a very gross scale. And if you look at the diagram on the left-hand side of the graph there, what I'm showing is part of a pre-drill program that was constructed using this seismic information. And the way that the depths are computed is by converting the amount of time that it takes for the sound to go down to the formation and come back to the surface into a distance. And to do that, you have to know how fast the speed is through these various formations. And that's under the control of the model that you've used to construct that. And it's not perfect. It's good and it's helped the industry immensely, but it's not perfect because we don't know exactly the speed through various pressures and fluid formations, et cetera, as we go down. So this advancement here is taking these receivers or these geophones that I said that were on surface and installing them in the drill string. And that gives us the ability, as we're drilling into the formation, to directly measure how long it takes for these signals to go through the formation. And as a consequence, as we're drilling ahead, we can take that information, send it to an onshore facility, in this case an onshore operations support center, and they can very quickly take that data and then recalculate or recompute the exact depth of where we're headed in the formation before we actually get there. And the model becomes more and more precise as you get further and further into the Earth. As a consequence, in this particular example, we have this formation of interest, which was originally picked at 30,000 feet, has actually been migrated up to 29,000 feet well before we actually got there. So I think a good analog to this is like headlights, at night. Without them, there's very little that you can see. With them, you still don't, see the mountain range that's 10 miles ahead, but you can certainly see around the corner before you get there. But the real point of this, and this is just one example, is I feel that an area of technology that I think is quite important is the understanding of where it is that you are before you actually get there, so you can design that into your programs well in advance. The example I gave earlier, exiting the base of salt. If you're prepared for that, an operator can quite easily and safely and consistently make it through the base of the salt. If you're not, it historically has caused problems in the past. Looking forward, I think as mentioned even by Director Bromwich here earlier, there is no doubt, I shouldn't say there is no doubt, but there is a very good chance that we're going to go deeper. We're going to go for older geologic time horizons. And when you look at the technology, at least in the sector of the industry that I'm involved with, that has implications for sure. One, just around what I just described, we're going to have to image deeper with higher resolution, and that will be a challenge. But another more practical matter is that the pressures, and in some cases the temperatures of these formations are going to be higher and hotter. So the tools that we use to acquire this data and to drill this, and also the way that we complete these formations, are going to have to be capable of doing so in those higher pressure, higher temperature environments. So a big part of our new product development program, and certainly the new research that's gone on in the industry, is around exactly that, is developing the higher pressure, higher temperature equipment. And you'll see that quite a bit of that has already come out over the last several years, and much of it is to come as we go forward. So I would be, I realize this is a technology panel, but I'd be a little bit remiss if I didn't discuss, at least in one slide, process. And here I'm discussing competency, process, and adherence to standards. So firstly, in the area of competency, so there are regulations, at least in terms of well control around competency, but I also feel that it's an area that we need to improve upon. Historically, saying that we need people with 15 years or 20 years of experience is not enough. I believe that we need people that are specifically trained and can demonstrate that they are proficient in operations in these environments. And certainly deepwater certification is one. And having a systematic competency management system, I also believe, is quite important. With regard to process, having an ISO type program, which to demonstrate consistency is quite important, but I also believe it's is as important or more important to ensure that each project that you embark on, in each task that you go with, has a readiness assessment, and that we've appropriately assessed the risks of the job. With regard to accountability, we're firm believers that everyone should be accountable to adhering to the standards. And I hope that everybody in our industry now recognizes that they are empowered to stop any job that they see or feel is not safe, and they're capable of keeping it stopped until they can demonstrate that it's safe to proceed. That's something that you'll hear over and over again from the operators in this room, and as well as the contractors as well. And I suspect we'll hear some of that in the final panel. With regard to standards, in Dr. Beck's presentation, he talked about barriers earlier, and we're undergoing a company-wide look at all of the barriers that we're responsible for in all well operations, not just deep water offshore. We've identified an excess of 60, and we've created a universal standard to ensure that everything that we're doing is designed to the same criterion, and that even perhaps more importantly, we understand the interfaces between various barriers and how they're meant to be working with each other. Lastly, there was some discussion around SEMS or SEMS, the Safety Environmental Management System. I would say that we strongly support that. I believe it goes into place in November 15th. It's based obviously on API RP75. And for me, it's, we had discussions around, is the regulations keeping up with the technology? And having an appropriate safety environmental management system in place gives everybody the tools, if you will, to self-regulate and ensure that as we introduce new technologies, we manage that change appropriately. So my last slide really is this summary. And what I'll say is, technology has gotten us a long ways. It has obviously advanced us from the early days of the piers that we built offshore to where we are today. And I stand by my statement. The technology that's in use today is extraordinary in deep water offshore. The quality of the information and the interpretation of the subsurface, I think, is quite important in the context of making sure that we understand what we're getting into before we get there. Equally important, of course, is the hardware that was talked about earlier today in terms of containment and prevention. And then lastly, technology is quite important, but if it's not underpinned by consistent processes and standards, technology alone is not going to get us there. So thank you very much.
For your time, can we just go ahead and dispense with the questions? We need to get one more speaker in.
Okay.
And have a panel discussion. Thank you.
Yep.
Our final speaker is Dean Newkirk. He is the Cullen Trust Higher Education Endowed Professor in Department of Electrical and Computer Engineering at the University of Texas, Austin. So, Dean, thank you.
All right, one more person to figure out which button to push. Which button is it? That arrow, right arrow, okay. There it goes. Good afternoon. When I sat down to try to figure out what to say this afternoon, it was kind of a challenging audience. Rather than leaping into incomprehensible details that would bore even me, I tried to step back and wanted to talk a little bit about sensing, and that's basically what I do. I do sensors of all sorts. And I tried to step back from it, though, and just kind of ask questions about what does this mean? And obviously, in the context of the Macondo, how do you prevent a problem? I'm not a drilling engineer, but when I read the report, the first two things that bothered me were the float valves and the positive and negative pressure tests. And when I get to sort of classes of sensing, I'll come back to that. Obviously, you could prevent the cause, right? That's what we'd all love to do. That does imply you know what the cause is. And it also implies you know what to do to prevent it. And you have to be a little careful, because if you apply a preventative measure for something that isn't there, you may do more harm than good. So there's something you've got to detect. Or you can remediate. You can do prognosis. You can look for a minor problem and try to stop it from becoming a major problem. In either case, you have to see, in other words, you have to sense something with sufficient warning time to do something. And in the sensor world, we refer to that as a sensor actuator pair. You also have to communicate the information from the sensor to some sort of controller for the controller to take the action. And so that communications channel is pretty important, and the intelligence in the controller is pretty important. Now, to figure out what my targets are, what are you trying to sense? I'm looking for defects. You know, you've got to even think about what are the classes of defects. So are they, as the first one, are they point defects or are they distributed? Are you looking for one little thing? A float valve is one little thing. Do you know where the defect is? Do you already know it a priori ahead of time? By design of the structure, for instance? Or do you have no clue where it is? How many defects are you looking for? One, if let's say they're point defects, one or a whole lot? And how often do they occur? Once, or all the time, or once a month? All of these things lead to a lot of situations if you're trying to try to design a new sensing system. The easiest case would be a small number of isolated defects where you know where they are. So by design of the structure of the well, hopefully you know where the float valves are, although you might not even know that. Cracks in structures. If it's a designed structure, then you probably know where the high stress regions are. You know where to anticipate cracks, so you put a few sensors there. The hardest case, I think, is the case where you have the possibility of many defects, you have no idea where they're going to occur, and you have no idea how often they're going to occur. Now, if it turns out there's only a small number of them, you might find them. With only a moderate amount of work, if there's a whole lot of them, and we just saw an example of this, when you start looking, you have to use a model to back calculate what happened. And you always get less data than you need. That's undersampling. And that means that there are always uncertainties. And then, of course, the question is, how bad are they? Ultimately, this comes down to seeing the defect or its cause. And so you need a sensor, you need a way to communicate that information to the controller. Two basic types of sensing: remote or standoff detection. We just heard the example of acoustic detection. That's a standoff detection technique. You still have to have a receiver someplace. It could be relatively complex. It might be on the surface. It might be in the wellbore. But you have a receiver. You do have to know the path, and the example we just got was if you don't know the path, you don't know what's going on, so you iterate back and forth. That's a good idea. But it requires you to be able to communicate through some medium, and that's one of the big problems, is that communications channel that you use to get information back and forth through. It's all about how good that channel is. Okay? Examples: vision and hearing. You know what the problems are with vision. I can present you with an optical illusion, and what it is and what you see are not the same. Same thing with hearing, obviously. The medium impacts things. If you look at a pencil stuck in water, it looks bent, right? Because you don't know what the medium is. So there are real problems in using remote sensing. It's great if you can do it, but it's highly dependent on the communications channel. Point or local sensing is nice if you can do it because it's where you need it to be. It's usually the highest sensitivity. You still got to figure out where it is if you didn't put it there ahead of time. If you want to do a big structure, you'll need a lot of point detectors, though. So there's a complexity there. The communications channel still has to be there. You got to get the information from the sensor to wherever you want to use it. There, the examples I use are touch and smell. Your finger is a point sensor. It feels where you touch. Your nose is a point sensor. It detects a molecule that has been transported to your nose. The quality of this communications channel, though, is extremely important in determining where the sensor can be relative to a problem, how big an area a sensor can see, and how smart the sensor has to be. And I'll come back to that in just a sec. Now, here's an ideal sensor actuator pair. Self-healing materials. It's great if a material fixes itself. So you want a material that's made out of has components that respond to damage to repair that damage. And if you want to think of it this way, it has a lot of point sensors in it, and it has a lot of actuators in it. Now, the separation between the point sensor and the actuator is probably fuzzy, if in existence at all. Example of this is so-called autogeneous self-healing in concrete. That's been studied for over, now 90-ish years for frost damage. And there's been a lot of interest in this, and Schlumberger has a new product, the future self-healing cement technology, which has materials added to it that expand when exposed to oil or gas to try to plug the crack if there's a void or a crack that forms later. It's a great example of what you'd really like if you can get it. Now, another issue here is what can we manage to do? And I do a lot of work in civil infrastructure as opposed to oil exploration. And in that case, one of the standard statements is with power and money, you can sense just about anything. Now, by power, I mean how much power you have to run it. By money, I mean how much it costs to install it. In civil infrastructure, money is a big determiner of what you'll put into a civil structure. If you're doing remote sensing, you probably have a complex receiver. Your eyeball is a pretty complex receiver. In terms of the power issue, though, if you've got a bright enough light bulb, you can see through even muddy water, at least a little ways. So there's still a power issue when you deal with a bad communications channel for remote sensing. For point sensors, the traditional way in the oil business has been to use wireline tools. The nice thing about wireline tools are that essentially you have a really good communications channel, the wire, and you have an easy way to supply power to the tool, the wire. So wireline tools are really nice, again, if you can use them. I don't know exactly how you use a wireline tool during a cement job. I just don't see how you can do it. I don't think you do. But if you can get away with the wireline tool, it's great. To do the cement survey after emplacement, it's a wireline tool, an acoustic wireline tool. The other possibility is you try to go for something fancier, which is a completely autonomous system, a complete sensor package that has no external connection to the outside world. And if you try to do that, it's all about power. The power budget is everything. You've either got to put a battery on it or it's got to scavenge energy from the environment, neither which are very good. You just don't have much power to work with. Another possibility is you try to have a sensor package that doesn't carry its own power or scavenge it locally. You do it remotely, and a good example of that many of us are familiar with are RFID tags, toll tags. Toll tags are powered by the transmitter that you drive under. The problem with those are that using the conventional way to do this, which was RF power, in the conductive earth, you can't transmit RF signals very far. In seawater, you lose an order of magnitude every foot if you happen to be using 1 megahertz, just as an example. But if you can get away with it, it's a nice way to do things. Lest we think we're the first people to struggle with some of this, there was a 1994 National Research Council study on drilling technology. This was published back in '94. I put the red box on there in terms of things that they identified at the time. And I think a lot of this has occurred, especially drill bit positioning and steering. Directional drilling is amazingly advanced. But some of the other things on there I think are still a bit unknown. There is another consortium that's kind of working on a related issue. This is the Advanced Energy Consortium, of which some of your companies are members. This consortium is focusing on pre-competitive research, primarily done at universities, in nanotechnology materials and sensors, but the focus is recovery, not the drilling operation itself, but recovery. And it's really pretty exclusively to recovery. I happen to have a project under this flag for doing sensors that we would want to put into formation, although near the borehole, and hence the title. Just as an example of the kind of things that you can try to think about, it's not directly applicable, but not completely inapplicable. Here's a civil system, bridges, concrete. And if you look down on the lower right-hand corner, you'll see an example of corrosion damage in a bridge pier. And what the interest is to detect that before it causes spalling, before the concrete falls apart. And we've done a lot of work with these sensors that have to be placed in concrete to try to come up with a way of a reading through the concrete to detect corrosion, for instance. We've also done conductivity and some other things. But it's an example of trying to come up with sensors that you can use in a harsh medium. We've done other work on similar sensors. The middle one is from an explosives detection program for the Navy's counter IED program. The lower one is one of the ones we're working on for the AEC, all designed to have some chemical sensing capability read at a distance. Other things that we might try to play with, the cement job was clearly an issue, and one of the questions is, can you put something as an admix? Well, ideally you'd like it to be an admix in the material, but could you put sensors in the cement? It's a tough problem. Can you instrument the casing? And that also, I think, is a real problem from the perspective of placement and damage done during the drilling operation. I think it's going to be a really hard problem, but one well worth looking at. Doing all this, you've got to know where, if you're placing these sensors after the fact, for instance, mixed in the cement, you pump it in. If you don't know where things are, it's not going to do you any good. And knowing where is a really hard problem from an instrumentation perspective. You need position and time. And what that all leads you to are systems which can fall on this graph, and I'm going to stop with this one, where you have a sensor package that you might like to deploy and a means of communicating with it. If the communications channel is good, the air in this room is really good for me to see you and you to see me. That's a good communications channel. Then the burden is on the communications channel, acoustic signals in a formation. Okay? In that sense, the sensor out at the other end can be something simple like a dye, if you can see the dye. If, on the other hand, the communications channel is not so good, so you're somewhere in the middle, then you have to put more burden on the sensor package, and that's going to get harder. If you're in the earth, where the only thing that propagates very well is acoustics, and even that can be challenging, then you've got to put everything here. And one of the things we're struggling with is trying to figure out a way of, honestly, finding a different communications channel. Because the complexity to get up here is daunting, to say the least. It's much better to be in remote sensing if you can, but the problem there is the communications channels are limited. We're interested in trying to explore other ways of communications. And that's my last slide for today. Thanks.
Thank you. Then let me ask the speakers to come take the seats while we have some specific questions for the current speaker. So the floor is open for the specific questions to Dean. Any questions? Okay, then Okay, so what we're going to do now, you've heard from all of the speakers about some of the new technologies. Now this is an opportunity to hear from you, and you ask these speakers that maybe beyond what you heard them speak, what do you think it will be the new technologies that will make offshore operations safer in the future? And so we have 2 microphones. Please go use the microphone and ask your question to the speaker, and we'll let whichever of the panelists that wishes to respond to answer to your question. So the floor is open.
This question is for Gene. A lot of discussion about overpressure and underpressure tests and anomalous results. What sort of hypothetical or ideal sensing technology would you think would have prevented that, where you weren't relying on indirect pressure signals at the surface?
Well, I think the analogy, the obvious problem is that both the negative and positive pressure tests, which were being used, among other things, to try to figure out whether the float valves had actuated, is huffing and puffing on a 5-mile-long soda straw that leaks along its length. it's a remote sensing technique, and it's amazing it works as well as it does. I'm just amazed that doing flow rates and pressure at the wellhead basically you can infer as much as you can. Ideally, there should be a trigger detector on the float valve that tells you it's worked. Right, when you remove the tube. Now that means it's got to communicate back up, right? And I don't know how to do that yet. I mean, maybe it's a mud pulse, although I'm not exactly sure how to pull that off either. But I think you need a point detection method. I don't think any remote sensing tool is going to be good enough to tell you what happened at something as small as a float valve. By that point, you're what? I'm not a drilling engineer, about 12 inches diameter at 5 miles. You know, a spy satellite can do that when they've got really good air to look through, but not looking through the earth. I think there's got to be something integrated at some point. We've got to figure out a way to put a sensor on the float valve.
More questions? Yes.
Yeah, I'm DeForest Ralph for the gas price report. In space travel and pilots, they use a lot of flight simulators and things of that nature. And I was wondering, to what extent do they have a simulator for offshore drillers that can simulate all these different kinds of problems so that the operators can get experience and get their intuitions and reactions developed, but also maybe even be a qualifying or a certificating technique to make sure if you put the guy to the test, if he doesn't pass, then he has to go back and learn how to do it.
My initial response is that the drilling contractors do have this type of apparatus. The problem becomes being able to program and foresee the scenarios accurately in the simulators. Most of the time, the simulators that people are using is for the physical functioning of the equipment, how to move the pipe in and out of the well, how to make connections, as opposed to responding to the downhole conditions. So I think that's an area that could be improved on quite a bit in terms of coming up with better simulators for actually creating unknown conditions for drillers all the way up through the tool pushers and the company men to learn to respond to. Right now, that's an experience-based training, right? That you're relying on people being in the job for a length of time to learn to recognize those types of situations and how to deal with them. And that's, to me, a pretty big problem in the business as we have a lot of crew turnover at the driller and below level, and we're having people turn over at the supervisory position simply due to age right now. So,
I've got a question for Gene Beck. Initially, it's probably going to sound like a rather controversial idea, but I'd like to get your thoughts on applying a technology that's typically only used in the onshore environment as a potential barrier to uncontrolled flow, a new barrier. In the offshore, we're dealing with world-class reservoir rock where we try to control any kicks with a mud weight that balances whatever pressure we're seeing. And that's worked very well in the offshore environment because the reservoir quality is so good. In onshore, as we drill poorer and poorer quality rocks, what we're starting to see a lot of is underbalance drilling. And in underbalance drilling, instead of having a mud weight where the goal is to prevent a kick, you are actually intentionally allowing the well to flow while you drill. And the way you do that is you set up at the surface with separators that have the capacity to handle flow while you're drilling. And we're using separators that can handle 100 million cubic feet of gas and 40,000 barrels of liquid, while drilling. And I'm not suggesting that we drill offshore wells underbalanced, but what if we drilled offshore wells with a surface setup as if we were drilling them as an underbalanced well, so that if the well kicks in an uncontrolled manner, we're able to handle that without having to shut in the blowout preventer. Just want to get your thoughts on whether that technology would be applicable in the offshore environment.
I think that where you're going, maybe not underbalanced, but I think the two technologies that are being introduced into the oil field right now, even on a commercial basis, one of them is managed pressure drilling, where the process is to understand entirely the pressure response of the wellbore throughout, so that you understand what pressure fluctuations mean in the wellbore, and then you can manage the amount of overbalance that you're drilling with. And instead of saying underbalance, minimize the amount of overbalance, can be a very effective way of getting casings in place, for instance, in the wellbore, to the tune where you have a much better casing seat at a much more optimum position, to where if you did have a well control incident, you would be able to control it, or to prevent the other end, meaning lost circulation, which is a severe problem in the deepwater wells as well. So managed pressure drilling is a technology that's coming along, as is dual gradient drilling. And I think both of those technologies, where you're looking at changing the basic hydraulic system that we've traditionally used, are going to be players in the future. The problem becomes it takes 10 to 15 years in the industry to get new technology introduced and accepted across the board for being used. Both of these technologies are well into that cycle, and I think that those are coming as probable regular usage technologies in all phases of drilling, not just deep water or onshore.
Are those still utilizing atmospheric gas busters, or is the flow contained?
Yeah, no, they could still be using contained flow devices at the surface. Okay.
I have a question. I've for Professor, for the whole panel, really. One of the challenges is going to be to make the Boomer a world-class regulator, which is really a partner and peer of the industry. Now, two of you are executives of big companies, and two of you are professors at world-class petroleum institutions. Where are we going to get the people? How realistic is it? I mean, we're going to need thousands of people to create a world-class regulator. How are we going to do that?
Yeah, from Exxon, yeah. That's a great question, and it's one that the industry's struggling with. And not so much specific, to the question of how we're going to get people to be experienced and talented and help us from a regulation standpoint, but just in our own business. You've heard the term, the great crew change is coming. So we're all struggling with that from an industry perspective. In my company's case, we've devoted a substantial amount of effort, more than what would normally be the case, to addressing that through training. And that may sound cliche, but in this case, it's how do we deliver training and on-the-job experience in a manner such that we are able to bring someone's capability to an operable level sooner in time than we have done historically. And so far we've been fairly effective at that. Now, is that going to be enough? Time will tell. Time will tell. I suppose that the regulator will have to adopt some sort of training mechanism that achieves a similar goal. I suppose the regulator may be looking to experience-based personnel elsewhere in the industry, possibly, in order to meet its need. But it's not just a singular regulatory issue or an individual company within the oil and gas spectrum issue. It's an industry-wide issue.
At Texas A&M, we limit undergraduate enrollment to 600 undergraduates in the department, and we turn students away. So, we could, we could have a student population much larger than that. The problem becomes we don't have a faculty large enough to manage that number of students. The other problem that I see is, working in the oil industry is a very highly technical job. It takes years of experience to reach competency to be a good drilling engineer or production engineer, what have you. And we get students for 4 to 5 years to get them a bachelor's degree. Well, the learning that they're doing, you still have to start from point A to try to get to point Z. There's just not enough time to progress the students to these higher levels of learning. The industry is the one that's providing the second stage of their education. And I think that we might be able to short circuit the time that it takes for an engineer to become competent in the industry through graduate education. But that has not been accepted in the oil industry very well at all historically. No, there's no need to get a master's degree. Well, if you can get a master's degree in 3 semesters and progress to senior engineer in 3 years instead of 7 years, I think it's a very good investment. And I think these are the types of things that the industry is going to have to start rewarding students for coming out of college with even more education than where they are right now. I think kids are very well educated. They have a lot of tools, but there's so much to learn when after 4 years of college that it takes years of training to get useful in these companies, and we've got to shorten that period of time.
Thank you. But with that, I believe we better bring the panel to the close. So thank you. Then we'll be continuing at 3:30, which is only like 10 minutes away, so that please be back as soon as you can.